This is the video on energy. So remember, in the video, there are going to be some codes. One will be a written code that will pop up on the screen. The other code will be a verbal code said by myself. And you will need both of these codes in order to move on with any subsequent homework assignments. All right, so remember, when you're looking at this video or you're looking through the slides, write what's in green, right? There's a lot of good information on these slides and in this video, but the way to distill it and put like really the important things, the big bullet points, write what's in green. So this is the weekly review written code. I would recommend you write this down somewhere. So let's just think about holding a rubber band, right? So let's just look at a rubber band. Does a rubber band contain a force when it's just sitting in somebody's hand? Now, does the rubber band contain a force if you bend it back and place it on your finger like you're going to point it at somebody? And then if you pull it back, why would you flinch if someone's pulling back a rubber band and pointing it at you? Why? What about a candy bar or a battery? Do they contain forces? Now, you recognize that all of these objects contain something, but it's hard to say whether it contains a force. Now, they possess something, but they do not possess a force. You cannot possess a force. You can only exert a force on something. A force is part of an interaction. It's not a physical entity that can be owned. Now, all of these contain something, and the question is, what do they contain? And I'll give you a hint. It begins with an N and ends in a G. Energy. Sort of a little bad joke there for you. Energy, right? So I said it starts with an N, ends in a G. Energy, right? That's what they all contain. Now, the concept of energy is not an obvious concept at all. In fact, it took us humans thousands of years to understand it. Not even the great and brilliant Isaac Newton was able to wrap his mind around it. He disagreed with it. He worked a lot with momentum and was like, I think momentum's good enough. Now, here's a thought experiment, right? Describe the color red without naming an object or showing or pointing to anything. Or pretend you're describing the color red to someone who has been blind their whole life. How would you go about that? Now, energy is like the color red. You know it when you see it, but you can't touch it, taste it, hold it, smell it, hear it, or even explain it very well. Energy, like inertia, is something that a body can possess, but it's not something that is tangible. So here's another thought experiment. Like, let's just take a look at the brick. Now, there are two things that you can do to a brick to make somebody fear for their safety, right? You could hold that brick over their head. They would get a little bit nervous. Or you could throw it, right? You could throw that brick. We call that ability that brick has to cause you harm, either due to the location or location of force field, is called energy. Energy is the capacity to do work. Now, all forms of energy are scalar, which means only magnitude, no direction. Now, the unit for all forms of energy is the joule, and it's represented by the capital J. Now, there are four basic ways of storing energy: potential, kinetic, internal, and rest mass. Now, these are split off into different categories as well, but these are the main four ways of storing energy. So let's take a look at these different forms of energy. Let's take a look at a rock falling down, right? What gives that rock potential? Right. So if you were dropping a rock in the water, what could you do to make that splash bigger? Well, what you could do is you could increase the mass, get a larger rock, or you could increase the height from which it's dropped. And the last one, this one's kind of tricky. You could go to a planet with a stronger gravitational force. Gravitational potential energy is potential energy at a height, right? And that's the equation for that. Gravitational potential energy equals mass times gravity times height. And the strength of gravity is 9.8 meters per second squared. Now, this is another form of potential energy. We have elastic potential energy. So I show this clip of somebody using a slingshot to launch a watermelon. And it's like, what could you do to make that watermelon go faster? Well, you could stretch that water, you could pull that slingshot back farther. You can increase the distance at which that object is stretched. Or you could just change out the band. So to make that watermelon go faster, you could increase the displacement of the band, like how far back it's stretched, or you could change the type of band, maybe get a thicker band. So elastic potential energy is energy stored by stretching or compressing an object. It's also compressing an object as well. Think about a ball that you drop and it bounces. That ball is going to compress, and that energy stored is, or that energy is stored as elastic potential energy. And this is the equation for elastic potential energy: 1/2 times the spring constant times the displacement squared. So it's technically sort of stretching out those elastic or the electric bonds between those atoms and molecules, but we just say it's stretching and compressing an object. Now, let's answer this question. How could a ping pong ball hurt you despite its low mass? And that brings us to kinetic energy, right? Kinetic energy is energy due to motion, right? The motion of an object. So now, if we look at this person getting getting hit in the face with a ball, what could you do to that ball to make that hurt more? Well, you could increase the velocity, how fast it's going, but you could also increase the mass. Now, kinetic energy depends on the velocity and its mass. So it's 1/2 times mass times velocity squared, as you can see in that equation. And kinetic energy depends more on the velocity because the velocity squared. The velocity has a larger impact on the kinetic energy of an object. That's why, like, if you hit a small ping pong ball at somebody, it can sting because it's moving really fast. Now, let's go over chemical potential energy. Chemical potential energy is energy stored in the electrical bonds between the atoms. This is the type of energy that is stored in foods that you eat, gasoline in your car, and the batteries in your phone. So this type of chemical reaction is more in chemistry, but you can see here that you're breaking those bonds. That energy stored, that's where you get all of your energy. You eat food, your body is really good at taking that energy stored in food, breaking those bonds apart and releasing that energy. And that's how we move. That's how we heat our body. That's how we think. That's where we get our energy. Now, let's answer this question. Why is it easier to stand in cold air than jump into water, even if they're at the same temperature? So that brings us to internal energy. Internal energy is the energy that can be stored within all the molecules of an object, like the motion of an object. Now, temperature is not directly proportional to internal energy, since temperature measures only the average translational kinetic energy of internal energy. Two objects with the same temperature do not necessarily have the same internal energy. So let's take a look at like what that means and why why you can walk outside in the cold, right? So you can walk outside, you can take the trash out, and you're just in shirts and a short, or a t-shirt and shorts and like sandals. You walk out to the garbage can real fast, even though it's like freezing outside, you're going to be fine. But if you fell into water of the same temperature, you're going to be at risk of hypothermia. Now, and that's because if you see over here, gases don't have a lot of places to store that energy. So when you walk outside when it's cold, yeah, you feel that cold. Some of your energy is being transferred to the gases outside, that air outside, but it's not going to be able to take it away that fast because it doesn't have a lot of places to store that energy. Now, liquids and solids do. That's why if you fall into water the same temperature and it's freezing, well, you're going to be in danger because there's a lot of places that liquids can store energy, and it's going to take your energy away really quickly. Now, here's another thought experiment, right? So let's just say you open up an oven, right? So if you open up an oven, like it's at 450 degrees Fahrenheit, you stick your hand or your head in there just to see, if whatever you're cooking is done cooking. Well, that hot air is going to hit your face, and you're going to step back for a second. Well, that air is at 450 degrees, but you're not really burned. You just sort of take a step back. Now, if you took your hand and you grab that metal grate, well, it's going to hurt a lot more. They're at the same temperature, though. You're going to have a burn because of that, and it's because that air, when it hits your face, well, it is at a high temperature, but it does not have a very high internal energy because gases can't really store energy that many places, but solids can. That's why even though the air and the metal rack are at the same temperature, they don't have the same internal energy, right? That's why just getting hit in the face with some air from the oven, you just sort of step back and you're a little uncomfortable, but you grab that metal rack, you're going to get burned really bad. So how does the sun keep generating its energy? That brings us to rest mass. So the last way of storing energy is rest mass. Now, you probably recognize Einstein's famous equation, E equals mc squared. Rest mass is the energy stored in the mass of all matter. So energy equals the mass of an object times the speed of light squared. So essentially just matter is mass. Energy is matter, or mass is energy. You can transfer, you can go back and forth between those two. And there's a lot of energy stored in mass. In fact, most of the energy that you interact with on a daily basis originated from the sun's rest mass. What it does is when it fuses it, it's taking that mass and it's converting it into energy, and it's released as like that radiant light and heat, and it goes out and it heats the earth, and that's where we get the majority of the energy from rest mass. And also it comes from, that's where nuclear bombs come from, right? That's where the energy is stored. And what it's doing is, if you think about the Hiroshima explosion only converted 700 milligrams of mass. That's about the third of the mass of a dime. You take that much mass and you convert it into energy really quickly, it's going to create a very large energy release in the form of an atomic explosion. So now that we learned about all the different types of energy, let's talk about the law of conservation of energy. So essentially, it just states that energy cannot be created, cannot be destroyed. Those are the two things that you cannot do with energy. But energy can do a couple things. You can transform into other forms of energy, and it can also transfer from place to place, like to a different object. So now that we know all of these forms of energies, I had this energy chart filled out. So you can see here, yes, there's like electric, light, thermal, sound. Those are forms of energy, and we're going to get to those later. We learned about internal rest mass and chemical potential. Those are forms of energy, but they are not mechanical energy. And the reason why I like this chart is because it really organizes it in terms of what is mechanical energy and what is not. Because mechanical energy is sort of a special kind of energy, and that's the one that you look at the most when we're like transforming in between those. So you can see here the forms of mechanical energy are kinetic energy, gravitational potential energy, and elastic potential energy. So that brings us to mechanical energy. Well, what is mechanical energy? So mechanical energy is energy due to the position of something or the movement of something. So there are three forms of mechanical energy: kinetic energy, gravitational potential energy, and elastic potential energy. I like to think of mechanical energy as the energy that's, you can recognize it the easiest. So what that means is that, like, if something's being thrown at you, you know it has kinetic energy. You're trying to duck out of the way. If something's being held above your head, even though it's not moving, you recognize it as having that potential to fall down and hurt you. And elastic potential energy, like if somebody's stretching a rubber band and pointing it at you, you recognize that it does have that energy, that potential to hurt you. That's what I think of mechanical energy. It is the energy due to the position or movement of something, but I like to think of it as it's the easiest form of energy to recognize. So these are the equations that we've already seen for all forms of the mechanical energy. So kinetic, gravitational, and elastic potential. Mechanical energies can be transformed into other forms of mechanical energies. So if there are no losses due to friction, then the total mechanical energy is conserved. That's what that last equation down there states, right? So you have the mechanical energy is going to be equal to the kinetic energy plus the gravitational potential energy plus the elastic potential energy. At every single point, you add up all three of those, my total mechanical energy is going to remain the same because energy cannot be created or destroyed. So these are the equations for it, and you can combine them all together, but we've already seen these before. So that brings us to the popper lab. So I have a popper right here. In a popper lab, the popper is just something that you can bend back, you set it on the table, and it pops, and it pops, and it goes up in the air. This is a very great example of energies being transformed, right? When it's bent back, it has all that energy as elastic potential energy. The instant it pops, it transformed into kinetic energy. And as it's moving up and it reaches its peak, well, that is when it has all gravitational potential energy. But at every single point, no energy was being destroyed or created. It was just transformed from elastic to kinetic to gravitational potential energy. But my mechanical energy, the total amount remained the same. So what happens to an object's kinetic energy and gravitational potential energy as it falls? So that brings us to energy skate park. So what you can see in this one is there's a skater going up and down the ramp. And this does a very great job of showing the kinetic and gravitational potential energy. It goes from gravitational potential energy to kinetic, kinetic to gravitational potential energy. But at every single point, the total amount of mechanical energy remains the same, but the different forms of mechanical do change from kinetic to potential, potential to kinetic. So do you trust the laws of physics, right? So that brings us to the pendulum here, right? So when a pendulum is swinging, at what point is it going the fastest? Well, the pendulum is going to be swinging when it's at its lowest point, and that's because it has transformed the most amount of mechanical energy into kinetic energy. Now, the pendulum is going to be going the slowest when it's all the way up, at the top, right? The highest point, because at that point, all the mechanical energy is kinetic energy. And in fact, it's at rest. So without any external forces, the pendulum could never go higher than that initial point, the initial starting point. And that's because energy cannot be created. It's never going to be able to go beyond that point. So that's the bowling ball demo, right? So when you see this, you might have seen videos of this, and you can see that in that little clip. But what you do is you take like a bowling ball that's on a string, you put it to your nose or your chin, and you let it swing, and it's going to come back. Now, it's not going to hit your face if you have it in the same spot, because it's never going to be able to go beyond that point, because energy cannot be created. If all that energy is gravitational potential energy, it can't have more than that unless somebody pushes it. So this is that bowling ball demo that you've probably seen before. Now, let's switch to roller coasters, because roller coasters are a great example of mechanical energy transforming into other forms of mechanical energy. Why is the tallest point on a roller coaster that initial drop? So what type of mechanical energy, like if you look at this cart, you can see here that this cart at the very top is going to have gravitational potential energy. As it's going down the track, it's going to have kinetic energy as it goes down the track, because it's transforming that mechanical energy from potential energy to kinetic energy. But notice the total mechanical energy does not change, and that's because energy cannot be created or destroyed, right? All it's doing is it's transforming from different forms of mechanical energy. Now, you know this cart's going to be going the fastest at the bottom, because that's when it has the most amount of kinetic energy. It's going the slowest at the height, because that's when it has the least amount of kinetic energy, the most amount of gravitational potential energy. So this does a very good job of showing energy transformation. So at this time, I'll go ahead and give you the verbal code. The verbal code is 335. I say that again. The verbal code is 335. So let's take a look at a problem that can be given. So at what point is a marble going the fastest? It's going to be the lowest point, right? So C and E are at the lowest point. They're going to be going the fastest. The marble is going to be going the fastest at that point, and it's because it has transformed the most amount of mechanical energy into kinetic energy, because it's at its lowest point. Low amount of gravitational potential energy. Now, at what point is the marble going the slowest? It's going to be point A. At point A, it's going to be going the slowest point, because it's at the highest point. Most of that energy is gravitational potential energy. Now, instantly looking at the points on the track, the marble is going the same speed, C and E, because they're at the same height. If they're at the same height, that means they have the same gravitational potential energy, which also means they have the same kinetic energy. Now, I could also ask you to rank the points along the track. The marble will be going the fastest to slowest. All you have to do is go from bottom to top. So it's going the fastest at C and E. Those are tied because they're at the same height. Then D, then B, then A. right? If I said slowest to fastest, you just go from the top down. It's going the slowest at A, then B, D, and C and E are going the fastest. Now, last thing is, without any external forces, will the marble ever be able to go higher than point A? No, because if it starts at rest, all that mechanical energy is gravitational potential energy. It's never going to go beyond that point. So here's another example, right? So this one's just sort of like that, but you know that it's going to be going the fastest at point C. That's the lowest point. You know it's going to be going the slowest at point A because that's the highest point. More gravitational, less kinetic energy. And if I ask you to rank this, fastest to slowest, you just go from the bottom up to the top. So that's C, E, D, B, F, A. If I ask you to go to the slowest to the fastest, you just go from the top down to the bottom. Right? That's how you can easily look at a roller coaster and tell, well, where's the fastest point? Where's the slowest point? And I can instantly rank them. So once again, as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.